Modern software systems process millions of asynchronous operations across the network every second. When thousands of devices suddenly reconnect and try a sync at the exact same moment, the resulting surge of traffic is chaotic. This uncontrolled burst of simultaneous data uploads spikes database CPUs to 100% capacity. The server freezes, drops requests, and ultimately crashes. To organize this chaos, back-end architectures rely on a specific structural buffer, the queue data structure. Without a mandatory buffer to catch and sequence erratic traffic spikes, scaling distributed cloud applications to handle real-world volume is impossible. This animated diagram illustrates the core operational principle of a queue: first in, first out, or FIFO. Elements are processed in the exact sequence they arrive. It operates on the identical logic of a waiting line at the DMV or document spooling for a printer. The priority is strict fairness and order, rather than the raw speed of any individual task. By enforcing this rigid sequence, the FIFO pipeline prioritizes overall system stability and predictability, absorbing massive volumes of requests smoothly. This diagram shows the mechanical structure of a linear array queue. It relies on two required tracking variables: a front pointer marking the position for deletion, and a rear pointer advancing to mark the position for insertion. Developers manipulate this structure using three essential operations, shown here in C++. The push method enqueues a new element at the rear, front peeks at the first item in line, and pop dequeues it. Because the queue functions by simply moving these front and rear pointers, rather than shifting massive amounts of underlying data, these operations execute in O of 1 constant time. This constant time complexity guarantees that data operations remain instantaneous. The execution speed is identical whether the queue holds 10 elements or 10 million. This linear array has a critical flaw. Moving the front pointer leaves behind unusable memory, eventually hitting a hard limit. To solve this, a circular queue mathematically wraps the rear pointer around, dynamically reusing empty front spaces. This structural evolution maximizes server memory utilization, preventing arbitrary overflow errors while perfectly preserving the critical O of 1 execution speed. Beyond simple FIFO, modern operating systems implement priority queues. Built on heap data structures, these variants allow highly urgent tasks to bypass the standard line and be processed immediately. This logic scales to the most intensive computing environments, from AI data pipelines continuously feeding expensive GPUs to network routers executing round-robin packet scheduling. Queues act as the primary traffic controllers, dictating the flow of both digital logic and physical hardware infrastructure. Returning to the threat of server crashes from chaotic data bursts, inserting a queue permanently eliminates this synchronization bottleneck. Software engineers rely on these structures to coordinate asynchronous execution, build resilient applications, and guarantee no request is dropped. By forcing strict mathematical order onto chaotic, concurrent requests, queues serve as the critical backbone that allows modern tech platforms to survive real-world scale.